Let's practice graphing a rational function together. In this particular example, we have the function f of x is equal to this 4x squared plus x minus 2 over this 4x minus 3. Now the first thing we're always going to want to do is see if we can factor this rational expression, either the top or the bottom of it. If we take a look at the numerator here, this trinomial, we actually can't factor this just because if you multiply 4 and negative 2 together, we get negative 8, and there are no two numbers that multiply to negative 8 that add to get that b value of positive 1 in the middle. Now on the bottom, this is already linear, so we can't actually factor this. Now the reason why we would check to factor is just because if we could factor and then cancel out some terms on top and bottom, that we could discover a hole for this function. But since we can't for this particular problem, we're actually not going to have a hole. All right, so we can't factor, so we're not going to have any holes for this particular rational function. Let's move on to the x-intercept. Now for the x-intercept, that's going to be when y is equal to 0. Our f of x is essentially y, so let's go ahead and write this out. So to find that x-intercept, we're changing this y value to 0. Now what's going to make this whole right side of the equation equal 0? Well, if this whole numerator is equal to 0, then 0 divided by the bottom is always going to be 0. So we can actually just ignore the bottom and set the top equal to 0 and say 0 is equal to this 4x squared plus x minus 2. All right, so we said earlier that we couldn't factor this, unfortunately, so we have some other methods. We could either solve by maybe square roots or completing the square or the quadratic formula. Now for this particular one, I think I'm going to go with using the quadratic formula. So for quadratic formula, we have x is equal to the opposite of b, which is going to be negative 1, plus or minus the square root of what? We're going to have the square root of this 1 squared. That's b squared minus 4 times a times c. A is going to be 4 here, and c is going to be negative 2. This whole thing is going to be on top of 2a, so that's going to be 2 times 4. Now this 1 squared is just going to be 1, and then we're going to have this negative 4 times 4, which is negative 16 times negative 2, which is going to be positive 32. So we're going to have 1 plus 32 inside. So let's see, x is going to be equal to, let's go ahead and get more space here. That's going to be equal to this negative 1 plus or minus the square root of 33. And then if we look at the denominator here, we just have 2 times 4, so that's going to be 8. And so keep in mind that when we had y equal to 0, this is going to be our two different x values that we have. We have our plus or minus version. So what are our x-intercepts going to be? Well, one of them is going to be negative 1 plus the square root of 33 over 8. That's comma 0. That's one of the x-intercepts. And the other x-intercept is going to be negative 1 minus the square root of 33 over 8, comma 0, right? So those are going to be our two x-intercepts. Now for the purpose of putting this on a graph later, if we go ahead and throw this into a calculator just to get an approximation, we're going to get that that is going to be roughly, I guess, 0.6, and go to the nearest tenths place just to make the graphing a little bit easier. And then let's see this other one. If we go ahead and plug in this negative 1 minus this root 33 over 8, we're going to get negative, let's see, negative 0.8 roughly. Okay, so if you want to be more accurate, then go to the hundredths place or thousandths place, but I think it's going to be pretty accurate. All right, so remember these are going to be our approximations here, but let's go ahead and just put in our x-intercepts and write those and say we're going to have a roughly 0.6 comma 0 and then roughly negative 0.8 comma 0. All right, now that we have our x-intercepts, let's see if we can find our y-intercepts. All right, now when we're looking for a y-intercept, that's going to be when this x is going to be equal to 0. So let's go ahead and take our function and plug in 0 in for x to see what y is going to be. So let's go ahead and take f of 0, right? If we take f of 0, that's going to be 4 times this 0 squared plus 0. If we go ahead and plug in 0 in both locations and the numerator, and this whole thing's going to be on top of what? That's going to be 4 times the 0 and then minus 3. Okay, so let's see what that's going to be here. On the top, we have 0 squared times 4, that's still going to be 0, plus 0, that's going to be 0, and then we have minus 2. So we're going to have a negative 2 in the numerator here. And then in the bottom, we have 4 times 0, which is 0, minus this 3, which is going to be negative 3. All right, so what is our y-intercept going to be? It looks like it's going to be a positive 2 over 3, just because a negative over negative is a positive. So we just found out that when x was equal to 0, that f of 0, or the y value going with it, is 2/3. So we're going to have our y-intercept be the 0 comma positive 2/3. All right, so we have that one y-intercept. Let's go ahead and just figure out where our table is here and then put in that point of 0, 2/3. All right, so we have our x-intercept done. We have our y-intercept done. And we said at the very beginning that we weren't going to have any holes for this particular function because we weren't canceling out any of those x value terms on the top and the bottom when we tried to factor. All right, so now time to move on to our asymptotes. So let's check out vertical asymptotes now. All right, moving on to the vertical asymptotes, that's basically when we can't divide by 0, right? So we just have to take a look at the denominator of our function, and we have to see when that's going to equal 0, because that's kind of going to be our number that we can't actually have x equal to because we can't divide by 0. So whenever you're finding the vertical asymptotes, just take your bottom or denominator of the function and set it equal to 0. So it looks like we have a linear denominator, so we're only going to have one vertical asymptote here. If we go ahead and add 3 to both sides, we're going to have 4x is equal to positive 3, then divide both sides by 4, right? So we're going to get x is equal to 3/4. So that's the equation of a vertical line, and that would be our vertical asymptote. So I'm going to go ahead and write that down here, x equals positive 3/4. That's the only x value that the function can't really compute here because we're going to have a vertical asymptote there. What about the horizontal asymptote? Well, let's take a look and see if we can see anything going on with the degrees of this function. So for the horizontal asymptote, we're going to go ahead and take a look at the highest degree and the highest degree of the top and bottom. So remember, for the horizontal asymptote, we only care about the term with the highest degree on top and bottom. So I'm just going to go ahead and copy those down. And it's just because as x becomes larger and larger, all the other terms don't have as much significance here or impact. So we're going to have this 4x squared over 4x. All right, I'm going to actually write 4x to the first power here. This is where you want to remember to look at these degrees over here. If these were the same number, then you would just take the ratio of their leading coefficients. If the bottom number was bigger than the top number, then the horizontal asymptote is going to be at y equals 0 along the x-axis. But in this particular case, we can see that 2 is greater than 1, or the numerator's degree is greater than the denominator's degree, and that means we're not going to have a horizontal asymptote. So we're going to go ahead and say that there's none here. All right, but there is going to be something that's interesting is going to happen in just a moment. But for the horizontal asymptote for this particular function, we're going to say that there's not going to be one. All right, so finally that brings us to our slant asymptote, okay? So when we're dealing with these types of functions, we want to take a look and see something very particular with these, and that's going to be with the degrees here. So when the numerator's degree is exactly 1 higher than the bottom, or the denominator's degree, then we're actually going to have a slant asymptote. Alrighty, so for our slant asymptote, what we're going to do is we're going to do polynomial long division. Let's see, we're going to take this one over here and divide by this one over here. Now, because the degree of the numerator is exactly 1 higher than the degree of the denominator, when we divide, we're always going to be getting a linear quotient, which is going to be the equation of a straight line, right? So that's going to be a diagonal line for our slant asymptote, all right? So let's see how many times does this 4x fit inside of this 4x squared. I think we've just multiplied by 1x, it's going to match. So I'm going to go ahead and put an x over here. We take the x and we multiply and distribute it to this 4x and then minus 3. First, we're going to get this 4x squared, and then negative 3 times x is going to be negative 3x. All right, let's go ahead and give those a hug and then subtract, see what our remainder is going to be here. 4x squared minus 4x squared is going to be 0. And then this x, take away a negative 3x. It's become just x plus 3x. That's going to be 4x. And then bring down that minus 2 at the end there. All right, so now what are we going to put here that multiplies by 4x? That'll match this 4x, and that's just going to be a positive 1, right? So put that positive 1 and then distribute it to that 4x and then that minus 3. That's going to be a 4x and then minus 3. Give those a hug, make sure we subtract the entire expression there. 4x minus 4x is going to cancel out and be 0. And then we have this negative 2 minus negative 3. That's just negative 2 plus 3, and that's going to be a positive 1. So we can just go ahead and say that our slant asymptote equation is going to be y is equal to the x plus 1. That's all we really care about from this, is just going to be the top. You can go ahead and ignore that denominator, okay? So let's go ahead and just take that y is equal to x plus 1 and say that's going to be our slant asymptote. All right, time to start graphing now. Let's start with the asymptotes. All right, so for vertical asymptote, we have x is equal to 3/4. Then we're going to go ahead and skip over the horizontal asymptote. That one's fine. Then moving on to the slant asymptote, we have a y-intercept of +1. So I'm going to go ahead and plot that down first. That's going to be right here just about. And then our slope is going to be this 1 in front. So it's going to be up 1 over 1. Let's go ahead and put that right over here. Up 1 over 1, just like this. We can also go down 1 and to the left 1 as well. And so drawing a dotted line through each of these points, we're going to see this would be where our slant asymptote is. Now for these x-intercepts, I'm going to go ahead and plot this -0.8, 0 first. That's going to be on this really close to the slant asymptote right over here. That's about -8/10, I guess. And then this +6/10, 0, that's going to be somewhere over here close to the vertical asymptote, right? A little more than halfway through this box, so something like that. All right, now what about the y-intercept? That's 0, 2/3 or 0.67 roughly, so 0, 2/3. I'm gonna plot that right about here, maybe 2/3 of the way up through this box here. And then for the y-intercept, that's 0, 2/3 or 0.66 repeater or 6/7 roughly, so 2/3 up the box, maybe something like that would look good. All right, so I think we can see the clear path of where the points are going to be connecting on the bottom part of this function. So I'm going to go ahead and draw a rough sketch through that. So this is going to be where part of our function is going to be. And for this particular video, I'm not going to go ahead and make a table to get some more points, but you would essentially go ahead and choose x equals 1 and x equals 2, maybe x equals 3. But if we have this part of our function down here as this part of this rational function, then the next part of it is going to be continuing somewhere up here, right? It's kind of just a rough sketch. So I'm just going to make a really rough curve to help you kind of see that, but feel free to make a table to confirm that. All right, again, this part is definitely more accurate, and then this part over here is less accurate, just a really rough sketch. Feel free to make a table to get some more exact values there, but hopefully this gives you a general idea of what it should look like. So there you have an example of graphing a rational function. This particular one didn't have any holes because we couldn't factor anything and cancel anything out, but we did have those x-intercepts and y-intercepts. There was no horizontal asymptote for this case, just check out those degrees. The vertical asymptote is when the bottom's equal to 0, and then the slant asymptote occurred here because the degree of the top was exactly 1 higher than the degree of the bottom. So hopefully you found the video helpful. If you did, please consider giving the video a thumbs up and sharing with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing, and I'll see you in the next one.